here, which is way heavier than when he left here at Moss Landing. Brent was my first grad student ever. He came to us from Kansas and decided to study the oceans. He was out at, let's see, where are we at? Truman State until 2001. Somehow ended up on the West Coast the year I got hired. Somehow figured out, apparently, that when you get hired, you have a little bit of money for students. So I'm at UC Davis doing a postdoc. Brent gives me a call and says, hey, I'd love to be your student. Want to have a beer? Drives out to Davis, has a beer with me. I didn't realize they'd already told him I had money. So he showed up. I don't even know if he wanted to do algae at that point, but he ended up becoming my first student to come in, my first student to publish. He actually has a paper published. If you guys remember Gustavo Hernandez Carmona, who was here as a visiting scientist, that was Brent's first publication, which is published in the journal that I'm now editor of. He went on to do good things. He went on to work in various aspects within Elkhorn Slough, on to do his PhD at UC Santa Cruz. His postdocs were in Fairbanks. And then also the Smith Conservation Research Fellow at UC Santa Cruz, the Friday Harbor Postdoc Fellow at Friday Harbor, and then now most recently has been hired on as a brand new, newly fledged assistant professor at Sonoma State, which is wonderful to have him so close. And you know, I was going through this whole thing and looking at lots of papers, lots of fun stuff. He's done a really great job, and I stop and think, you know, it was like one of my first kids who's gone off and done things. And you know what usually happens is when your kid turns 18 and leaves, they go get a tattoo, right? And it's usually something you didn't want him to do. So what does Brent do? He leaves Moss Landing and he goes and works on sea otters. Of all things to be working on in my laboratory, he goes on to become relatively famous working on sea otters. Luckily for us, Brent really never left the autotroph perspective. And so I think his sea otter perspective is very well-rounded in regards to thinking of both the bottom-up and the top-down components. And having him back here in the state of California working at Sonoma State, where he's going to have lots of opportunities to work in a lot of different ecosystems, is really great. So we're going to welcome Brent back up here to the stage to talk to us about, he just changed his title as well. There was something otters in there somewhere, but he's going to talk about the Elkhorn Slough system and other estuarine systems and how top-down predation helps to reflect balance in these systems. So thanks, Brent.
Thanks, Mike. Yeah, I had to I realized that I had an old slide for some sea otter talk, and I realized that it was in the same title that I was giving you guys for the advertising year. So apologies, this is not all about sea otters. There is a good amount of sea otters in here though. But first I want to ask you a question. What is an alligator? And you know, being here at Moss Landing, you're probably not thinking about alligators too much. I had the opportunity to think about alligators a little bit when I was at Duke University, because the folks I was working with worked on alligators, and they were finding some really interesting things. When most of us think of an alligator, we think freshwater swamps, the Everglades, Florida, the Gulf Coast, and we're primarily think of them as a freshwater species. But what if I've told you that alligators can not only move into the ocean, but they can actually thrive there. They can feed on things in the ocean like sharks and crabs, and they can actually make a really good living. And this kind of challenges the paradigm in alligator physiology, because alligators are thought to not to be able to process salt in their glands, because they don't have any sort of glands to process that stuff. But they're really good at hunkering down. And so it's not like alligators are these highly mobile predators that are just moving around like a sea otter all day eating things. No, they just sit there and do nothing until something comes in front of them and they eat it. And so they're able to concentrate salts, and then when they're done eating in the ocean, they actually move back into their little freshwater holes where they can start releasing and diluting all the salts they accumulated. So what is a river otter? Well, traditionally, how did river otters get their name? Well, they live in rivers, right? And they are specialists at eating fish in freshwater systems and also invertebrates like crawfish. But what if I was to tell you that there are entire populations of river otters that only live in the ocean? And this is the case in places like Drake's Estero up north where river otters are starting to recover, and they're starting to use marine systems just as much as they use freshwater systems, and they're really thriving on these systems. And I studied these otters a little bit in Friday Harbor too, and that's another place where the Friday Harbor and the San Juan Islands river otters really behave much like sea otters. And then, so, question for you, what is a sea otter? And we all know sea otters as, the kelp forest animals, the keystone species of the kelp. And but most of us now know that these are not just kelp forest animals. And really the prime example comes just right here from Elkhorn Slough. These animals are capable of using non-kelp forest habitats, and they actually can thrive in estuaries like seagrass beds and now into salt marshes. So a lot of these, what we once thought of as kind of a rare example of top predators moving into areas that we're not accustomed to, we're starting to see this happen more and more and more. Where we're seeing these top predators, and through conservation measures, they're starting to use habitats that we really didn't consider before. But now we're starting to realize that their niche breadth is a lot more expansive than what we originally thought. And really, these are bright spots in a period of time when we're experiencing a lot of doom and gloom, especially related to oceans and ocean conservation. And a lot of this has to do with the whole idea of a shifting baseline, right? So and I'm sure most of you are familiar with the concept of a shifting baseline. And this was a term coined by Daniel Pauly in 1995, a really famous fisheries ecologist. And he basically made the argument that as generations pass by, our kind of like our search image of what we think is normal changes. And so when you grow up and you go out and you catch some fish, you might catch a fish this size, right? And for you, you catch it, you're all excited, you're pumped up, it's a big fish. But if you ask somebody, you took a time machine and asked somebody several generations ago, they go, oh, that's a kind of a small fish. And so that's kind of what the idea behind a shifting baseline. Our perceptions of nature are ingrained in how we learned about nature and ecosystems when we were growing up. And so sea otters in California are kind of this rare example of a species that is in a state of recovery, and it's leading to a trophic upgrade to many different habitats. And what we're seeing with the trophic upgrade, the sea otters are really taking advantage of a lot of the estuaries, not only in California, but also throughout the range in like British Columbia and Alaska. And so some of my earlier research really looked at, well, how are these animals, these sea otters, behaving? What's their role in these systems? And what we found was that they have a really strong role. And in the kelp forest, they go for urchins, they go for tegula. In the estuary, they go for clams, and then they go for crab. And really the first thing that they go for in an estuary are the crab. They're really easy to catch. I don't know if you've been diving and seen a big red rock crab, how easy it is to grab. It has a lot of energy that the otters need. And so what we found is that when you have sea otters present in an estuary like Elkhorn Slough, where they can consume a lot of crab, they can have these trophic effects that trickle down all the way to actually the seagrass growing in the estuary. And the mechanism is that these crabs, especially cancer crabs, they get really big. They can eat grazers that live in the seagrass beds. And the grazers in the seagrass beds, they're really, really important because they eat algae that grows on the seagrass. So basically, they're like little lawnmowers. They keep it clean, and they allow it to thrive. And so what we've seen in Elkhorn Slough is a lot of this recovery has been tied with the resilience and the comeback of seagrass in the ecosystem. Prior to the 1980s, it was kind of in a state of major decline. It was almost gone from the estuary. It really has bounced back big time. especially in the most recent 5-10 years. And that expansion just keeps on going. It's quite phenomenal. I've never seen a system recover like this. There's some examples from the East Coast, like Tampa Bay and Chesapeake Bay, that have had experienced this, but this is a good example for our West Coast when we're really losing a lot of seagrass beds on the West Coast here. And so as we're doing this research, looking at sea otters in places like Elkhorn Slough, we're doing this research and we're following these sea otters, and we become accustomed to them like living in the seagrass beds and in the lower part of the estuary. But as we started following them more and more, we started noticing that they were using these other habitats that theory never even predicted they'd be able to use, such as salt marshes. And so right here is a video of a sea otter. This is shot with a GoPro. This is a sea otter in Elkhorn Slough in one of those tidal creeks, foraging on little pachygrapsis crabs, so our native common shore crab. And there it is, periscoping. It's consumed its crabs, and it's actually diving down and going to get more of these crabs that are hunkered down in these burrows along the bank. And there he is again. Okay, so a little history of Elkhorn Slough. I feel like I could speed through this stuff really fast because you're all really savvy Elkhorn Slough people. So as we know, or most of us know, 1946, a major alteration occurred in Elkhorn Slough where this opening was constructed by the Army Corps of Engineers to accommodate the harbor in Moss Landing. And they didn't have the sophisticated modeling techniques that we have these days, but it essentially created this fire hose effect where Elkhorn Slough all of a sudden had this huge tidal flux that was going in and out. The former mouth of the estuary before 1946 was right about here, about a kilometer north. And so this was like a slow meandering channel up to the 1940s, and it was, part of the year it was actually closed off, so there wasn't this exchange with the ocean. So now they put in these jetties. You have full-time fire hose effect going all day long. The system has been in an erosional state since then. And then on top of it, there's eutrophication. There's lots of algae that we think is fueling a lot of these shore crabs that we just saw the otter eating, pachygrapsis. And so they'll create these crab condos here, these burrows. And the burrows really destabilize the banks. This is pretty well known. There's a lot of work that's been done in the East Coast and Argentina, looking at marshes there and the relationship between crabs and salt marsh stability. And a lot of folks have been finding that crabs destabilize marshes when they burrow. And so in Elkhorn Slough, a very common feature, especially a couple years ago, when the erosion was really pretty much at its most severe, you'd go along the estuary and you'd see calving off of the bank. So big chunks of the salt marsh would just pretty much sink into the water. And so once that marsh is gone, it has a really hard time coming back, because there's a lot of things going on in the system beyond just the crabs, and beyond the hydrological alterations. There's also sea level rise. So the marshes are trying to keep up with sea level rise. And so once they lose big chunks of that, the chances of getting it back are pretty small. And on top of this hydrological alteration, there's been a cutoff of a lot of the freshwater sources in the estuary. And so there's not as much sediments coming in, so it's a sediment-starved system. And it really has disrupted this nice, what once was a nice, healthy marsh. And so what's unique about this newer discovery has been that we've been able to, because Elkhorn Slough is kind of a small system, we can really track the entire population of sea otters and have a really good handle on what's going on with the salt marsh over the entire landscape, the entire system. So that makes it really unique. And not only that, the sea otter density in Elkhorn Slough is the highest in California. So we have a really high density of these top predators in the system. And so when we started looking at this, and actually Ron's here right now. Ron was one of the guys who discovered these sea otters using the salt marshes. But when we first started seeing this, they're only using really a couple creeks, right? And so we're like, oh, this is kind of another one of those things like, it's kind of neat, you know, they're using a couple creeks. This is kind of weird. But over time, you know, they started using more and more creeks. And once we started seeing this, really a lot of light bulbs started popping up and hypotheses were being generated. And, you know, we got really excited about studying these animals. So we initiated a really big project in about 2014 that coincided with another big project looking at these sea otter, this particular sea otter population over a period of a couple of years, really intensively. So it meant we had 20 tagged animals in there. There were people almost out there on a daily basis throughout the estuary looking at foraging. So we have tens of thousands of foraging estimates in the estuary. And then every week or so, people would go out and count every single sea otter in the estuary. So we had a really good idea of where these sea otters were and when they were in the system. And then, to our surprise, the sea otters, we thought they would probably just use marshes rarely, or maybe they only liked a few of these tidal creeks. But by 2016, the sea otters were basically almost everywhere in the estuary, except for maybe around Hudson's Landing. And I believe today, now they're up and around Hudson's Landing. So they're really using the entire estuary. And it really has been a very fast kind of forward motion from around 2012 to 2016 up until today in terms of the distribution of sea otters in the estuary. So now they're using every tidal creek, but what's really cool about it is that they're using these tidal creeks at different densities. So it's like we can use that variation to ask some really neat questions, ecological questions about what their role are in these salt marshes. And so I'm just going to show you a couple of slides here of some of our results. And I call this slide the silence of the marsh because when we first went out there in like 2014 or 2013, you know, there was a lot of crabs out there. Elkhorn Slough had a ton of crabs. And you'd go out to the marsh, and you know, they'd be burrowing in the mud, and the marsh would create this percolating sound. It was like, you know, it's just like a bajillion crabs trying to breathe in the marsh. And it was a really distinct feature when I went there. I remember it was really kind of striking how loud some crabs could be when they're trying to breathe in the salt marsh. But now you go there, and after, you know, sea otters have been there for several years, it's almost like dead silence. And it's kind of eerie because we know that there were at least once were a lot of these pachygrapsis crabs in the marsh. So we started thinking, you know, okay, if they're eating these crabs are burrowing and creating this disturbance to the marsh. Perhaps sea otters could be having an effect on the salt marsh, and it could either be a negative effect because, you know, sea otters are big animals. They can get up to 100 pounds. They can haul out onto the pickleweed and onto the marsh, and that creates mechanical disturbance. But at the same time, they're removing a large amount of burrowing crabs from the system. So what is their overall effect has been a big question. So in each one of these points right here, so this data comes from some transect surveys that we did in every single tidal creek. And when I say every single tidal creek, I mean the majority of tidal creeks in Elkhorn Slough that are a significant width. So each one of those dots represents a different tidal creek. And we can get these great models. There's a guy named Tim Tinker who's a sea otter expert. Some of you might have heard of him. And he is a modeling guru, and he's been spatially modeling sea otters for a long time. So we're able to put together all that monitoring data to create these really robust estimates of sea otter densities in the salt marsh in each one of these tidal creeks. And then we look at crab densities in traps. And the way we do it is we take these tennis ball cans, empty tennis ball cans. You've probably seen those, right? And we put them in the mud, and they're kind of like flush with the surface of the mud. And then crabs, they fall in. They're just little pitfall traps. And so we spread these out across these tidal creeks, and we get a mean value of what the crab densities look like, and that's what you see right there. And there's nice, somewhat nonlinear relationship between sea otters and crab densities. And then so when we look at marsh edge retreat, and this is looking at each one of those tidal creeks, we looked using aerial imagery. We looked at the widening of these creeks. So that's the process of erosion can be measured by just looking at how fast these creeks, the rate of widening, right? So the wider the creek is over time, the more it's eroding away, essentially. And so what we see is that when you have more sea otters, you get less of this marsh edge retreat. And then if you look at the process, the underlying mechanism of what's controlling this, it really is this increase in salt marsh biomass in the below ground that's been really kind of positively impacted by sea otters moving into these tidal creeks. And so a lot of it has to do with what the crabs are doing. So they're burrowing, which is destabilizing the banks. But what we found through experiments, through feeding assays, is that they like to eat the roots of the marsh, of the pickleweed. And a lot of these roots in these estuarine wetland habitats, they store a lot of sugars in there, and so they're like these nice sweet snacks. And we think that the crabs really thrive off of those. They also eat other things like algae and stuff. So, but what we see here in Elkhorn Slough is that we have more sea otters, we have more below ground biomass. Okay, so there's two different things that we've been looking at in relation to top predator recovery and ecosystem function in terms of stability of shorelines and fish habitat with the seagrass. But what about invasion resistance? And there's a lot of theory out there on what makes a system less invadable. And there's actually a lot of debate. It's like, a lot of it is like, oh, if you have a really diverse native assemblage, then you can have less, or you'll have less invasions. Other people think that diversity means there's a lot more possibilities for an invader to move into a system. And so, what is it? What really drives a system from being invaded? And so we started thinking about this primarily after observations. And so when we were doing all this salt marsh work in Elkhorn Slough, one day at Kirby Park, I saw a single sea otter eat about 30 green crab, European green crab, in about 30 minutes. It was quite remarkable. And as you know, these European green crabs they're pretty nasty invaders. They obviously come from Europe. And they invaded the Atlantic coast first, and recently in the late 1980s, they invaded San Francisco Bay, and a couple of years after that, Elkhorn Slough, and they've really had a stronghold in parts of Elkhorn Slough for several decades. And so, again, light bulbs come up in my head, and I'm thinking, well, if sea otters what we know about sea otters is true, that they can eat about 8,000 crabs a year, and I just saw this one eat about 30 of them, maybe they can provide some invasion resistance to the system. And so what we've been doing is trapping green crab in areas with and without sea otters. And in Elkhorn Slough, you probably know, there's a railroad there, and it offers a nice kind of unintended experiment, because what it actually does for a lot of the estuary is creates a barrier for sea otters, where sea otters can't really cross the railroad. They will to some degree, but not all that much. So it creates these areas where you have these green crab strongholds and sea otters can't get to, and then other areas like the main channel, which have been green crab strongholds in the past, but now have sea otters because they've been recently moving up into where these areas like around Kirby Park where you have a lot of green crab. And so what we see in our crab traps for the green crab is that when otters are absent, the green crab are still sticking around. And then when they're present, they're pretty much all gone. And so we're starting to look at this now not only in Elkhorn Slough, but other areas throughout the coast that have sea otters, like British Columbia and other parts of California. And so just trying to look at this question of invasibility of an ecosystem. So what this all amounts to really is maybe not an entirely new coastal food web for sea otters, but once you start adding in these exotic species like European green crab that they eat, it really does become a new coastal food web, at least to science. So a lot of this research has come from Elkhorn Slough, and Elkhorn Slough is great, but it is kind of small, and so making generalities is well, we all know is a bad thing when when you've only studied one little area. And I think some of you taking, that's what you talk about first couple days of stats class, right? You have to really define your inference area. So, when these studies came out, especially the Seagrass one, it was like, well, are they doing this everywhere? And recently we were awarded, with folks from the University of Alaska Fairbanks, we were awarded an SF to start looking at a much larger area of Southeast Alaska. Southeast Alaska it's so different than California because there they have sea otters that are also recovering, but they're recovering really, really fast. And there's a lot of concern with the recovery of sea otters in Alaska because they eat a lot of the same things we eat. So the local populations in Southeast Alaska are pretty worried about it. But we're also asking the question of, okay, do they have similar effects that we see in California? And so, Southeast Alaska is huge. There's 28,000 kilometers of shoreline. And that's 2.2 times more shoreline than the lower 48 states. 1.5 times the size or the shoreline of Chesapeake Bay. But there's only 72,000 people. And most of those 72,000 people depend on the ocean for resources, especially with native communities that are dependent on things like clam and abalone and crab, all things that sea otters eat. And in terms of seagrass, this is a massive system for seagrass. There's about 16,000 kilometers of shoreline that have seagrass. That's more than all of the lower 48 put together. And it's really just a couple of species, Zoster marina and a couple of species of Phyllospadics. And remarkably, it has received very little research attention. It is kind of a remote area, so it's hard to get to, and therefore probably a lot less research has been going on there compared to California. But what's interesting is when we look at sea otters and their expansion into these seagrass systems, we see a very similar relationship with sea otters, and here is above ground biomass of seagrass. And so the sea otter index is something we have to do because this is such a massive system. We can't treat it like the coast of California where we can count every single sea otter in a couple days with an airplane. It's just not possible there. So we have to use indicators, metrics, different metrics of sea otters, such as, just focal surveys, one-time focal surveys, time since occupation. We can actually go to a beach and look at clamshells to see how many clamshells were eaten by a sea otter. Sea otters leave a really distinct signature in clamshells because their tool use. And so we can put all these together and get an index of what the sea otter population looks like at a bunch of different sites around. And this is primarily around Prince of Wales Island in Southeast Alaska. And so we see a very similar relationship. And right now we're trying to work out, okay, is it there's more seagrass because of sea otters, or is it There's more sea otters there because there's more seagrass. It's kind of a chicken and egg thing up there. And these are things that I'm not specifically spending all my time focusing on. It's a grad student named Wendell Raymond up at University of Alaska Fairbanks. So this is his PhD research. So a lot of the stuff I've been talking to you about today, it's all about what can estuaries do, what can sea otters do for estuaries. It seems like they can do a lot of positive things. But we're also asking this question, what can estuaries do for sea otters? And I don't know if you know the stories about sea otters recently. There is Southeast Alaska, British Columbia. The populations are recovering quite well, but in the Aleutian Islands of Alaska and in California, it's kind of a different story. And what the prevailing theory is that predation is really limiting these populations. So up in the Aleutians, it's thought that orcas have recently really taken off and really done some major damage to the Aleutian Island population. In California, it's great white sharks at outer end of the sea otter range. So just north of San Francisco is the northern extent, and then Santa Barbara is the southern extent. And a lot of sea otters end up washing up on the beach with great white shark bite marks. And so it's been demonstrated pretty well by Tim Tinker and Kevin Lafferty that it's really these white sharks that are preventing sea otters from expanding. And in California, it's important because they only have two directions to go in. However, when we think about estuaries, it's really cool because in Alaska, it seems like these estuaries can provide this predation refuge. So this Clam Lagoon, which is on Adak Island in the Aleutians, is this massive, really shallow coastal lagoon with lots of seagrass. And it's so important as a refuge for these sea otters that the population just in the Clam Lagoon has now exceeded that of the Aleutian Island population. So it really does indicate that it's a refuge. And same with Central California. Central California, you can see there's been kind of a plateau over the last couple decades for sea otter population. But on the bottom there is Elkhorn Slough. There doesn't seem to be anything stopping that. In fact, we think Elkhorn Slough is probably now at carrying capacity. So really, there's nowhere else for sea otters to really go for Elkhorn Slough. And the population growth rate has been phenomenal. So what can estuaries do for populations like sea otters? They can provide this refuge. Sea otters are now still endangered on the endangered species list. And so managers of the sea otters and ecosystems along our coast are concerned with, okay, the sea otter population and, how do we potentially increase it so it's not an endangered animal anymore. And so a lot of folks have been looking at San Francisco Bay as a potential area where we could put sea otters, or eventually sea otters might get there naturally. And there's, a lot of kind of historical precedents of sea otters being in San Francisco Bay. There was a great book written in the 1930s by a woman named Adele Ogden. It's all about the sea otter trade up until 1848. And there's some great passages in this book all about San Francisco Bay. And San Francisco Bay was a hub for sea otter hunting. But when the hunters, the European hunters, first entered into San Francisco Bay, it was covered in sea otters. That's how the story goes. So in this passage from Ogden's book, it says, in the bay from San Francisco to the estuary of Santa Clara, the ground appeared covered with black sheets due to the great quantity of otters which were there. And then they were even doing things like recruiting Aleut hunters from the Aleutians, because they were such good hunters of sea otters, they were actually bringing them down, forcing them to go down to San Francisco and help them harvest sea otters out of the bay. So we know that sea otters were once in San Francisco Bay. And what we can do is we can take the information from estuaries where sea otters currently exist, like Elkhorn Slough and Morro Bay, and we can use the habitat their habitats such as salt marshes, open water, seagrass, and we can start making predictions about how many sea otters can San Francisco Bay support. And so right here, you can see this is basically a map. In the green areas are seagrass, and the brown areas are salt marshes. And then the blue areas are basically open water. Much of San Francisco Bay is pretty shallow and reachable, and so for the sea otter, even within its diving depth limits. So a lot of this estuary can actually be used by sea otters. And so I didn't do this. This was, again, Tim Tinker. He creates these models and can make these really robust predictions about how many animals can a system like San Francisco Bay support. So our latest estimate is, on average, it could probably support about 5,000 to 6,000 sea otters easily. In the upper thresholds, probably the carrying capacity is more like around 10,000. So right now, currently in California, there are 3,000 sea otters. And so one system could potentially double or triple that population. And again, providing resilience to the population when they're stressed out by things like climate change or the loss of kelp or whatever you have. Okay, now I'm going to switch gears for a little bit and briefly talk to you about some of the other research I've been doing on the coastal nursery function. This is my favorite of all ecosystem functions. I don't know what yours is. It was carbon sequestration, but now it's the coastal nursery. This is really kind of still considered a hypothesis, right? It's a very elegant hypothesis. And the first kind of big paper that came out on the nursery function hypothesis was in a paper by Mike Beck, from the Nature Conservancy and a bunch of other people. And in it, they described what it takes to be a coastal nursery. I mean, obviously, people have seen in the field juvenile fish or juvenile crab using shallow coastal water habitats, and they kind of suspect that these could be important nurseries. But Beck et al. Put it into this kind of theoretical framework where they describe what you really need to become a nursery. And it's all about comparing habitats, different habitats that might have juveniles of a certain species, and kind of comparing them. And then ultimately, the ultimate goal is to figure out, well, are these really contributing to some adult population? And that adult population could be offshore, it could be inshore, depending on the species. So, one of our big questions recently, since this hypothesis is almost 20 years old, we wanted to reflect on it a little bit and see does it still hold water? Is this a really robust hypothesis that's kind of spanning the stretch of time? And so we did what's called a meta-analysis, looking at as many papers as we possibly could, looking at the coastal nursery function from around the world, and trying to determine, okay, where are we at in terms of the state of the knowledge of the coastal nursery function. And you can see we had a nice spread, a nice geographic spread here all over the world. And what we found was, the nursery hypothesis still holds water for certain habitats. Some others, not so much. And really the big winner is, in this case, is SAV, which is kind of a generic term for submerged aquatic vegetation. We try to call them seagrasses. But so SAV, seagrasses are really important. And then the typical players of mangroves and coral reefs are also important. But some of these other habitats, they kind of have these variable kind of effects on different parts of what you're looking at for a juvenile fish or crab. So if you look at density, growth, and survival, it's very consistent across seagrasses and mangroves to some degree. But then some of these other habitat types, it's not so apparent. And so on the bottom, just to explain to you what this is a log response ratio. So it's basically taking two different treatment types a control treatment and some other kind of treatment, and looking at it as a ratio, and then taking the log of that to get this log response ratio. So if you're on the positive end of things, so if you're on the right side of that line there, it basically means there's a positive effect from that habitat. If you're on the left side, then it's a negative effect. And kind of what struck me as really surprising, and I got really worried when we were starting to publish this, is this kelp thing. And it's like, wait a second, kelp is a negative effect on juvenile species? And this just doesn't seem right. Now, what we found is all the studies that came out of our Web of Science search for this meta-analysis came from the Gulf of Maine. So maybe that has something to do with it. But it also indicates to me that there's this data gap, this knowledge gap that might exist for kelp forest on the West Coast. So if somebody in Scott's lab maybe should start doing that. Or maybe you've already done it, I don't know. Mark Carr's done it. Yeah. So there's the one study from the West Coast, it was Mark Carr's study that we could find. But most of them came from Maine. So there's this big area of research that somebody could tackle in this room. And just looking at the nursery function of kelp. And I bet you'd find a different result from that. And so on the West Coast here, we have a little bit of envy with respect to this nursery hypothesis compared to like the East Coast and the Gulf Coast, where a lot of the earlier studies were done on nurseries. But there are a few species that we're pretty sure are really good candidates for this nursery hypothesis. There's several species of salmon. I just picked out Chinook because it's one of the most obvious. Flatfish, like English sole, are definitely a nursery species on our West Coast here, and then Dungeness crab. And here are just some studies that have documented this nursery function. But they're kind of just spread out, like all the Chinook salmon ones come from, well, some come from Central California, some come from Puget Sound. Dungeness crab comes from Oregon and Washington. English sole came from down here, and a little bit of Puget Sound. But there's this huge gap in information where we just don't understand if the juveniles that are using these shallow coastal water habitats are using them as a nursery, or is it just another habitat for them? And so we attempted to kind of summarize this information on West Coast nurseries using a systematic review of the literature. And this has been done before. So the earliest kind of attempt to summarize the nursery function was actually done in 1990 by some folks from NIMS. And so they basically went up and down the coast and they characterized all these different species that they think were good nursery habitat candidates, and they basically counted all the systems that had those species. More recently, Mary Gleason from the Nature Conservancy kind of repeated these efforts by Monaco and found a lot more of these nursery habitats up and down the coast. So this is basically Southern California to Puget Sound. And then our most recent review kind of extended that. We found a lot more estuaries compared to Monaco. Some of them, we had actually decline in minimal estuaries, but that's because we didn't include San Francisco Bay in ours. And Mary Gleason, in her 2011 synthesis, included San Francisco, and she basically subdivided San Francisco into a bunch of areas. But so what it comes down to is, like, every time we look at the nursery function more and more, we find more and more systems that could be these really important nursery habitats for these focal species. Now, one of the problems that we're facing with these systems is that some of them are really stressed out. And so this is the idea of multiple stressors. Some of you might be familiar with the Ocean Health Index from Ben Halpern's work. This is kind of like the Ocean Health Index, but it really focuses on estuaries more. This was done by folks at National Marine Fisheries Service in Seattle. And there's some really striking things that pop out with respect to the West Coast, especially the Southern California Bight is pretty impaired. Central California is pretty impaired. Oregon and Washington estuaries in general are doing okay. But then you get into Puget Sound again, and things start getting bad. And so this basically, it takes into account a lot of different variables, which include like land cover, and is there a dam in the watershed, and what's the land use like in the dam, what's the pollution like, what's the eutrophication like, and it kind of smashes them all together into one score for each system, and that's what you get. So we can take these scores and combine them with density estimates, or actually monitoring data from these various systems, and say, okay, are these multiple stressors, do we have any indication that they're having an effect on these nursery species? And again, the answer is, well, sometimes. The two main species where we see kind of these negative declines in juvenile fish are with Chinook salmon and English sole. And those end up being really kind of what the two poster children of the nursery hypothesis on the west coast here. But then there's other species like Dungeness crab. We know Dungeness crab use estuaries almost, not exclusively, but estuaries contribute a lot to the offshore population of Dungeness crabs. But we didn't find that multiple stressors were affecting the juvenile densities in these systems. So what is affecting, what could affect Dungeness crab in these shallow coastal systems? Well, we're finding that sea otters they can affect the nursery function, or potentially affect the nursery function. We don't have experiments showing this, but what we see is happening with Dungeness crab, and this data comes from Elkhorn Slough, and this is some work that's done by a San Diego State University student named Tracy Grimes for her thesis. And she's looking at it with a very similar lens. She's asking this question, okay, as you get more and more otter density throughout the estuary in these areas where we find Dungeness crab, what happens to their size, what happens to their density? And so what she's seeing is that these areas that are high density sea otter areas, she's seeing the crabs actually get smaller. And so if you think of it from the nursery function perspective, the crabs in the estuary, to avoid predation and to grow big, and before it moves out and becomes an adult. And so there's a lot of potential that sea otters are negatively affecting this nursery function. And that's important to consider when you're considering the recovery of sea otters. There's these positive effects, but again, there's going to be some negative consequences, and this could be one of them. So I'm going to wrap this up by going back to those original questions. So what is a sea otter? Well, I hope I've convinced you at this point that it's a kelp forest animal, but it's also an estuary animal. And that there's actually this brand new food web that's open to explore, looking at how sea otters impact these estuarine communities. So what is a river otter? Well, these are recoveries of animals into these novel ecosystems are creating these really bizarre food webs, such as this example from Florida and some mangrove area where a river otter is eating alligator. We have alligators eating sharks. We have alligators eating blue crabs. And then sometimes we have a sea otter eating an elasmobranch. So these food webs are becoming really, really bizarre, at least to us. But if you think about prior to humans moving into some of these areas, this might have been really normal. So are we going back to the new normal is kind of the question. So I just want to thank people on both sides of the research, Sea Otter Collaborators. That picture is a woman named Susan Williams, who is one of my postdoc mentors. Susan unfortunately passed away a year ago before we could wrap up a lot of the research we'd been doing together. So we miss her. And then got to give a shout out to Greg, Greg has been a lot of the inspiration for some of this nursery work, and it's because he had such a big impression on not only the labs here, but also Elkhorn Slough research, and he was really a champion of students getting out there and doing a lot of fish surveys, which I'm sure Scott's doing the same thing too. So, but then there's all these other folks who I've been collaborating with. And so my last message is a PSA, which I hope this is not rubbing you the wrong way, but just make sure you slow down for sea otters when you see them in the street. They're starting to cross the road in many of these places, going into now brackish water marshes, and so it's a fun time to be studying these animals because they keep moving into these new systems, and where do they stop? I don't know. They'll tell us. So thank you. Okay. Yeah.
Sorry, because I'm from the seaweed lab. I have a few questions about seaweed.
Okay.
I have two. My first question, when you're talking about the Alaskan slough, I guess.
It's basically
Marsh.
one big estuary.
Okay.
Yeah.
So, have you been seeing Ola there as well?
So the nutrients, the Ola's there. It's just not that.
Okay.
It's not that prevalent.
Okay.
And the nutrient concentrations are nothing like what we see out here in Elkhorn Slough, or even on the coast here, because of upwelling. There they have downwelling, so it's a totally different kind of dynamic.
And then I just have a question for you. The study that you did in Elkhorn Slough, comparing otters to no otters with the crabs.
Mm-hmm.
Is it possible, I'm trying to wrap my head around what you guys did to catch the crabs, but is it possible that it's just one side had the pressure from the predator and the other one didn't, and that's why the crabs maybe just weren't out as much?
Could be.
Where the
Yeah,
others
I mean,
were,
there's this
or-
whole, there's a lot of theory out there, new theory, that's all about the landscape of fear, and so there's a lot of fear. It's not just I eat this, it's the fear of getting eaten. There's a guy named Michael Heighthouse who is from Florida, but does a lot of work in Shark Bay, Australia, and they've shown this really well with tiger sharks, and how it's not so much the predation effects on like turtles and dugongs, it's more the fear, and so they'll use less optimal habitats to stay away from roving tiger sharks. And so it could be a very similar thing here. The crabs might just hunker down a little bit more. Yeah. So that's a good thought, and that could be. Yeah.
Does that 5,000 CRs in San Francisco number, is that a San Francisco that has people or humans?
It does, yeah, it does. Yep, that's a San Francisco of humans. And the thought is, like, especially for like seagrass habitat in San Francisco, there's a lot of people think it's about 10% of what it used to be. And so we think it's it's actually a conservative estimate. And the modeling that went into it used the lower thresholds of densities in Elkhorn Slough to make it even more conservative. We tried to make it as conservative as you possibly can. And so, yeah. And there's a student at San Francisco State named Jane Rudebush. She's an Ellen Hines student. And she's working on the risk factors associated with different human activities in San Francisco Bay, especially boat traffic and oil spills and things like PCBs and mercury in the water. And she's doing a really cool project where she's creating that kind of index, a risk index. And she's using that, all these risky things that could happen to sea otters to inform, well, if you did move sea otters in San Francisco Bay, where would you put them? And so we know where we would put them. We would put them basically in San Pablo Bay, kind of near Tiburon Marine Station. It's kind of like the least impacted. There's still some boat traffic, but there's a good amount of seagrass, not as much human activity. Because the other option would be like right out near Oakland, Berkeley, Alameda. They have really nice seagrass beds out there, but who wants to be out there? Yeah.
All right, so I'm going to remember back a couple, well, many seminars ago, we heard from Jim Malnavi talk about the kind of temporal variability in what otters eat as they move into a system. And,
Yeah.
he ended talking about how otters out in front of where he's been working, which is Hopkins forever, right?
Yeah.
Don't eat urchins anymore because yeah, and they moved on, right?
Yeah.
But they're still thriving and they're still part of the system.
Yeah.
But they don't eat what they were originally
Yeah.
eating. And at the time when otters had moved into that system, there was a lot of data showing the
Yeah.
crashes in the urchins. And so you showed this really nice graph which had some history to it.
Yeah.
And it was the seagrass going up and down and bouncing underneath it was the otters.
Yeah.
And you argued, well, they're probably not at carrying capacity, but at one point they will be. There will be only so many otters you can have in Elkhorn Slough.
Yeah.
And at one point, they'll be eating about as much crabs as they can possibly eat. And that's quite possibly going to be, the crabs probably won't be as important anymore and harder to find.
Yeah.
It's possible they'll move on to another prey
Yeah.
in the slough, right? So how stable is this dynamic, right? Because now you have this mental health forest off of Hopkins where urchins are eating kelp side by side with otters that used to eat urchins.
Yeah.
And you're describing a top-down consumer's role in thriving seagrasses as long as they eat the crab.
Yeah. And so, I think Jim was right, because in Elkhorn Slough, they'll deplete a population, not entirely, like, they won't drive a population to extinction. That's never happened with an otter, but they will drive it so low that they'll have to switch. And in Elkhorn Slough, they, after the crab, they switched to probably clams, and then they would exhaust them, and then we think more recently they started focusing in on fat innkeeper worms. That's their go-to now. And then that's a big reason why we think they were moving into the marsh is they've exhausted all the crab in the main channel, and now all of a sudden here's this big stash of these other crabs that are maybe not as ideal because they're a lot smaller than cancer crabs, but yeah. And so in terms of, and that's why we think we're seeing also these really bizarre things happening, like, eating round stingrays and leopard sharks, which, we really haven't seen too much before. And we've seen them, I think, eating birds? Yeah, they're eating weird things.
But birds usually is one otter that's picked up that
Yeah.
ability. It'll visit Elkhorn Slough and
Yeah.
so we'll have 2 or 3 birds. There was 2 in the last week.
Yeah.
And then it'll move on. But you can see more. I've seen a mother otter eating a grebe and sharing it with her pup. So they learn it. They're carnivores.
Yeah.
So my follow-up to that was if it's that dynamic, right? And I think you had one quote out of the book. I guess what I'm asking is, how do we know, or what evidence is out there that they did or did not utilize estuaries, prior to being very heavily predated upon by us, right? Which is
Yeah.
the late 1800s, late 1900s. Is there any evidence archaeological?
Yeah, there's a great archaeological record from primarily middens that go all the way back 10,000 years. And in each layer of stratigraphy, there's sea otter bones mixed with oysters, mixed with clams. The best one's probably the Emeryville shell mound, which is just layer and layer and layer of sea otter bones mixed with deer and oysters and all sorts of animals. So that's been the big evidence. But it's a shame because unlike Alaska, we've lost a lot of the traditional ecological knowledge that they still have in Alaska. So the natives still have these folk tales of sea otters being around, and so that rich knowledge still exists, but down here it doesn't. So we're totally reliable on archaeological evidence, which there's a guy named Jones. I don't know if anybody, I'm forgetting his first name. He is an archaeologist, and that's kind of what he's been doing for his career. And so he's produced this rich data of all these middens up and down the coast, characterizing everything in these middens. And sea otters are very common in the estuary middens.